Hello, everybody. We're going to go ahead and get started. Fantastic. Welcome to OpenAI Scholars Demo Day. Thank you all for being here this evening. We have 8 presentations tonight as a result of our Scholars program. We had 550 people apply and 8 scholars. So that makes us a bit more competitive than Harvard, but you know, we don't want to brag. Anywho, the scholars have spent the past 3 months studying machine learning full time. 2 of those months have been spent on a self-selected curriculum, going through the different skills that they need to be able to complete a final presentation, which they will be showing to you today. This is a project that they've completed in 1 month, which I've been told is a very short amount of time to complete a experiment in machine learning when you are just a beginner. However, they've been assisted by our really awesome mentors, who are a combination of OpenAI and external folks. And we're really excited to have everyone here. So I'm going to go ahead and pass it off to Ilya, who's going to say a few words before we get started. Thanks.
All right, hello, everyone, and welcome to the Scholars Demo Day. It's really exciting to see the projects that the scholars were able to accomplish in just 1 month. One thing about machine learning is that it's not the easiest field to enter without mentorship. And working closely with a good mentor can really narrow down the very big surface area of machine learning down to manageable pieces that make progress far more rapidly. And I can say for myself, I definitely wouldn't be where I am without the mentorship that I received. So with this, I want to say thank you and express real gratitude to all the mentors who helped bring the scholars to where they are right now. And finally, doing a project in just 1 month is not an easy feat at all. So congratulations to all the scholars who've done this, and let's see the projects.
Thank you for coming to our demo day. Today I'm going to talk about exploring gamma, the discount of the future, or the weight of the past. So here's a bit of background for those who are unfamiliar with reinforcement learning. It is a framework where an agent takes action in an environment to maximize cumulative rewards. So the measure we care about is the expected sum of total rewards, and the measure we actually optimize is the expected sum of total discounted rewards. So the difference of here is the discount. And not only it prevents us from getting an explosive sum to infinity, but also it injects some preferences, which I'm going to talk about. So what is discount factor? From economics, discount factor gamma specifies some intertemporal preferences. And what I mean by preferences is to imagine a thought experiment where if I hand you a full apple tomorrow, or some gamma fraction of an apple today, and then I twist the gamma until you find the single gamma that you are indifferent between the two, then this gamma reveals your preference. So with this preference in mind, let's look at a toy example in some simple grid war experiment. Here we have 2 agents. One has a low discount preference, so it will prefer immediate rewards, such as the coins on the left, which has lower value. Or the agent below has a high discount, meaning it will prefer long-term future reward, which is a diamond. So we can see different preferences results in distinctive behavior that the agent could express. As a beginner to RL algorithm, we may just ask which discount factor gamma to use. Well, some will tell you 0.99. Or other will say something close to 1. Not 1 for boundedness. And some will say, just try a set of gammas and pick the best. So none of these answers seem entirely satisfactory. So I found out this about Blackwell optimality principle. Actually says that in all environments, there exists an optimal policy that's simultaneously optimal with gamma higher than some threshold. So looking at this principle, we may find it quite intuitive because given some real-world environment where we always maximize cumulative reward, that applies gamma equals 1. However, in real world, we cannot use gamma equal to 1. But having a gamma of 0.99 results in a very similar intertemporal preference as a gamma equal to 1. Having a gamma 0.99 in the diamond case, in the real world case, the agent will still pick diamond over the coin, despite having a slightly lower discount factor. So the question I'm interested in is, do deep RL algorithms always find the Blackwell optimal policy for gammas above the threshold? Well, let's go back to this time. We use a lower exploration instead of high exploration in the previous case. And we see the behavior is the same for the low discount agent. However, for the high discount agent, it cannot obtain any reward. So not necessarily in this case that all deep RL algorithm could find this kind of optimal policy. So in this work, we'll demonstrate this issue and propose methods to repair it. To do that, I set up two real-world environments, one with sparse reward, the other with dense reward. So the agent in red is trying to collect all the yellow coins, which will give them positive reward, and they want to avoid poison, which will give them negative reward. And lastly, they don't want to get trapped, otherwise they'll die. So the algorithm I use is from baselines, OpenAI's baselines DQN. And then the experiment setup is I only vary the discount factor and keeping everything else constant. And here's the initial results on the sparse environment. So I pick a set of gammas from 0.2, 0.5, 0.8, and 0.99. As you can see on the right curve, the highest gamma, 0.99, yields the best performance. And it seems like there might be a threshold between gamma 0.5 and 0.8, such that above that, all high gammas yield optimal performance. So this is quite consistent with the Blackwell optimality principle. Let's look at how this will work in a dense environment. So here we see that the highest gamma, which is in pink, 0.99, is actually not doing well. It's not even doing as well as the gamma 0.5 in this case. So we see some inconsistency with the Blackwell optimality principle. Let's dig further. So after thinking about it, my hypothesis to this behavior is that discount factor may play a dual role in DQN update. And specifically, it not only explicitly specifies the intertemporal preferences, which is to discount the future, but implicitly it encodes some confidence on bootstrapping of the function approximator, which is to weigh the past. So I propose a time-varying discounting, gamma of t, so that when we specify a myopic fraction, that's some fraction of the total time steps, and during that period, we are going to vary our gamma from 0.1 to a final gamma that we specified, so that it have a linear schedule that we weigh earlier experiences less. The gamma will keep fixed after the myopic fraction. So using this simple scheme on the dense environment DQN algorithm, let's compare the experiments. So the pink curve is still the fixed gamma from the in the dense environment, and all the other colorful curves are with different myopic fraction. And to see this more clearly, I grouped all myopic fraction setups in a single block in blue, and then you can see all the myopic fraction, no matter how large it is, outperforms the baseline's algorithm with the fixed gamma. And because 0.99 wasn't doing well, and then with this initial myopia, it could actually become optimal. So this is a really good result. And let's see if it can work in the best gamma, which is 0.8 in the dense environment. So I do the same thing where the pink curve is the fixed gamma, 0.8, which was the best gamma in the dense environment. And all the myopic fraction are in blue on the right side. And then we see that any myopic fraction could eventually achieve the same level of performance as the original fixed gamma and just take longer. So what about the sparse environment? So I tried the same thing where on the, we have the fixed gamma. On the left, we have gamma of 0.8. On the right, we have gamma of 0.99. And you can see subsequently, as we increase the myopic fraction, the longer it takes to reach optimal, but they reach optimal nonetheless. So fixed gamma yields the best performance in this sparse environment, but all myopic fraction converge to optimal eventually, so it doesn't really hurt in the long run. So summing up from all these initial myopia results, we see that high discount gamma could become optimal with initial myopia. And the benefits of this simple scheme is that we don't need to fine-tune gamma because it improves learning in dense reward environment and doesn't harm learning in sparse reward environment. However, you may say that, oh, our hypothesis is that this initial myopia will mitigate bias, thus better performance. There might be a competing hypothesis is by introducing this initial myopia, you may have more exploration, which might lead to better performance. So I'm trying to see whether this benefits is a result of bias reduction or exploration. To do that, I set up three experiments where I fix the discount factor. And for the baseline setup, I have 0 myopia and low exploration. For the myopia setup, I have a low myopia and low exploration. And for the exploration setup, I have 0 myopia and high exploration. So to see the results, let's look at the plot on the left. Here, our gamma is fixed to be 0.8 across all three setups. And for the baseline, it is in pink. And then we see that it has similar performance as the myopia, which is in orange. And the exploration actually did worse than both of them because it takes longer. And on the right, we have a gamma of 0.99, which is considered the poor gamma in the dense environment. And we can see with myopia, it actually outperformed both baseline and exploration. And with the exploration, although it eventually surpasses baseline a bit, but still takes a long time. So we can sort of conclude that exploration helps, but not significantly, and it takes longer training time. But with myopia, it improves significantly and converges faster. So as part of the future directions, we try to formalize this dual role intuition and run more experiments on standard testing ground. And I will also want to compare a myopia schedule on lambda versus gamma in PPO. I have some initial results and happy to discuss offline after the presentation. So just a recap, here are some related works. And final takeaway, discount factor matters in deep reinforcement learning. And it has a dual role that it specifies intertemporal preferences and also encodes confidence on bootstrapping from function approximation. And a simple myopic schedule is a robust and effective way to improve performance. And the same logic may work beyond DQN and discrete action state framework. Thank you. I'm happy to take questions. Oh, yeah.
You mentioned that exploration helps early in training. Do you think it's possible to turn down the exploration over the course, so start at a very high level and then go to a low level, or would that have the same effect as what you did?
Yeah, so in the baseline DQN, they have this similar linear schedule for exploration, where it started low, started high, and then become low, and stay low for the whole time. Yeah.
Hello. I was wondering if you can think of a way. So I really like this idea of seeing gamma as something that kind of encodes your confidence. Do you think there's a way to kind of like take your uncertainty into account more directly? It seems like you're currently doing it over time, but do you think there's a way to like make that more explicit by, I don't know, getting some uncertainty estimate for your Q function?
Yeah, thank you. It's a really good question. I'm thinking to first try it on the generalized advantage estimate because it explicitly separates out lambda and gamma in the equation, where I feel like lambda is precisely the role it plays in confidence in bootstrapping. So I guess by varying lambda, perhaps in the algorithm of PPO, could help with this issue. Yeah.
Any other questions?
Oops. Oh, no, sorry. Good.
Okay, so I'd like to begin by thanking everyone at OpenAI who organized this event. You can't hear me. How about now? Okay. And I'd also like to thank all of you for attending. So previously, I was a PhD student at the University of Chicago, where I studied cell biology. But these days, what excites me most is the prospect of getting general purpose robots deployed in the real world and then getting them to do useful things. And so one challenge associated with this is that robots will have to learn how to solve new tasks with little to no external feedback. So for the past month, I've been working on a project that leverages a robot's internal motivation in order to overcome this lack of supervision. So I'll start by placing intrinsic motivation in the context of reinforcement learning. So in the reinforcement learning setting, you have an agent that interacts with an environment via its policy. So the policy takes in observations and it outputs actions. So at every time step, the agent takes an action and receives a reward from the environment. So by learning to maximize its total expected reward, the agent can find a good policy and eventually learn how to solve a given task. But finding a good policy can actually be very difficult when the rewards from the environment are sparse. So what we really need are reward functions that are intrinsic to the agent instead of relying solely on sparse extrinsic rewards. Okay, so how do you get dense intrinsic rewards? So there's actually been a lot of work in this area. But a lot of approaches center on some notion of novelty. So by seeking novelty, the agent is driven to explore, and in doing so, learns new skills that might help it solve a given task. And so this approach has actually had a lot of success recently with solving challenging Atari games like Montezuma's Revenge. However, these ideas haven't really been applied to robotics. So in this project, I'll show you how using a simple formulation for intrinsic rewards will lead to nice solutions for solving challenging robotics problems. So before I discuss the method that I use, I'll talk about the Fet Robotics Environments, which were developed in-house at OpenAI by Matthias, sitting in the back. And so the observations include the position and velocity of the gripper, and it also includes the pose, the linear velocity, and the angular velocity of any object that might be in the scene. The action space is continuous, and it's four-dimensional, and it includes the first three dimensions correspond to change in position along X, Y, and Z, and the fourth dimension corresponds to opening and closing the gripper. And so again, we care about the sparse reward setting. So here, the agent receives, at every time step, a reward of 0 if it solves the task, and -1 otherwise. And I just want to point out that for all of the environments that I'm going to talk about, which include reaching, pushing, sliding, and pick and place, the agent has at most 50 time steps to actually solve the task. Okay, so here's an outline of the method that I use. So the diagram on the left, you can see that it's very similar to the reinforcement learning setting that I talked about a few slides ago. But here, in addition to the agent having a policy, it also has a dynamics model. So the dynamics model takes as input the agent's current state and its action, and it makes a prediction for the next state. And I also want to note that we could set up the dynamics model to make predictions for the robot's change in state. And so here's the intrinsic reward. Here's the intrinsic reward that I'm using. And what you'll notice is that it's simply the prediction error of the dynamics model. And so larger prediction errors should lead to larger intrinsic rewards. And so the idea is that the agent shouldn't get stuck in regions that it's already explored, and instead will be encouraged to explore elsewhere. Okay, so for training, I use simple, fully connected networks for both the policy and the dynamics model. I trained the policy using PPO, which is an actor-critic architecture that was developed here by John Schulman. And briefly, since PPO is on policy, I use a number of actors in parallel to collect a large and diverse set of data that can actually be used to update the parameters of both the policy and the dynamics model. Okay, so here's my first set of results. So I'm applying this method to first to the simplest of the tasks, which is reaching. And here I'm comparing a baseline PPO implementation with no intrinsic rewards to intrinsic rewards that were generated by predicting the full next state or by predicting the change in state. And so for a simple task like reaching, it turns out that you don't actually need the intrinsic rewards, but adding them, you can see that the agent learns to solve the task much more quickly. And you can see in the bottom panel that as the agent learns, the intrinsic reward actually goes down. Okay, so I next looked at the pushing task, which is actually quite a bit more complicated than the reaching task. So unlike reaching, the baseline policy is not actually able to solve this task. But when you add in the dense intrinsic rewards, you can see that the agent quickly learns how to solve the task. And near the end of training, it's solving nearly 100% of the episodes. And so when I approached the pushing task, I actually looked at a number of different hyperparameters. And so I'll talk about 3 here briefly. So I looked at the size of the individual layers within the network. And as you might expect, larger networks tend to perform better than smaller networks. I also looked at the learning rate for the dynamics model. And so this actually turned out to be very important. So as you can see here, smaller learning rates tend to outperform larger learning rates. And the last thing I looked at was seeing whether or not resetting the environment early after the agent has already solved the task will lead to better performance. So that's what you can see here. So after the agent has solved the task, by doing an early reset, that leads to a significant boost in performance. Okay, so I next looked at the pick and place task. And this task is actually a step up in difficulty from the pushing task. But here the story is more or less the same. The baseline policy cannot solve the task, but adding in either intrinsic reward can actually lead to the agent learning how to solve the task. And for reasons I don't quite understand yet, predicting the full next state tends to outperform predicting the change in state. So that's something I want to look at a little bit more in the future. Okay, so the last thing I looked at was the sliding task. And it turns out that by comparison, the sliding task is probably more difficult than the others. And so here, I actually needed a larger network than what was required for the other tasks. And I also needed twice as many environment interactions for the agent to learn how to solve this. Okay, so to summarize, consistent with previous works, my results demonstrate that adding intrinsic rewards can actually be useful in solving challenging tasks with sparse rewards. Although unnecessary for solving the reaching task, adding intrinsic rewards as an exploration bonus actually leads to improved performance. And intrinsic rewards were actually necessary for solving the more difficult tasks. So in the future, I plan to look at slightly more complicated tasks such as tool use and block stacking. And I also plan to look at different kinds of inputs, both for the policy and for the dynamics model. And in particular, I'm really interested in looking at combining different sensor modalities. So looking at combining images with depth maps with contact information. Okay. And so with that, I'd like to thank Maddie for organizing the Scholars program. I'd like to show my appreciation to scholars, past and present. I'd like to give a special thank you to Matthias, Alex, and Lillian. They gave me really good feedback that I was able to use to make modifications to the fetch environments. I'd like to thank Yura, Harry, Igor, and Wojciech, with all of whom I've had really enlightening conversations. And I'd like to give a special thank you to Yura and Harry, whose previous work was actually the inspiration for this project. And last but not least, I'd like to thank my mentor, Fayal, who provided me with a lot of encouragement and support over the last couple of months. So, and with that, I'd be happy to take any questions.
Have you tried LSTMs instead of fully?
That's a good question. Probably when I start to incorporate different sensor modalities, I'll have to move to using LSTMs.
Also, it may help with the delta version of the inputs.
Yeah, it could. So I wanted to try it originally, but the simple method that I used already had such good performance that I'd sort of put that off. Yeah.
Any other questions?
Was there any stochasticity in the environment?
Yes. So every time the environment was reset, the target location would change. And if there were a block in the scene, the starting location of the block would also change.
Oh, I see. Was there any stochasticity in the transitions, like from one point in time to the next point in time?
So like this kind of movement, there was no stochasticity. The movements were completely deterministic.
I see. Gotcha.
Yeah.
Thanks.
How important was it to trade off the goal-directed reward versus the intrinsic reward? Like, did that require some tuning, or not so much?
I think most of that tuning came from tuning the learning rate for the dynamics model. Because if the learning rate for the dynamics model was too big, then the agent would very quickly learn how the environment worked. And so the intrinsic rewards that it would get would be really small. Whereas if you delayed that, it would get larger rewards early, encouraging exploration. But if you're referring to like the size of the rewards, the relative to rewards, say -1 versus what the intrinsic reward was, I did tune that quite a bit. Turns out 1 works really nicely, which offsets the reward of -1 from the environment. Yeah, larger rewards don't work in intrinsic rewards don't work. Yeah.
Any other questions?
Great, thank you.
Thank you. Hi, everyone. Thank you for being here tonight. And louder? Okay. Great. Is it any better? Okay. Thank you. So, welcome. So, I will be talking about my experiment with fine-tuning GPT-2 small model for question answering tonight. Before I start to talk about giving you the details about my experiment, I would like to mention the question that I was interested in, which guided me in my decision to work on this problem. One of the biggest challenges that we have in natural language understanding today is the ability to create systems that have common sense reasoning, which is the ability of an intelligent system to come up with common sense knowledge and reason about a given text. So this is still a notoriously difficult task, and although we have very high performing language models and systems today, we are still struggling to perform better in this one. So in this chart, you notice that there's an increase in the benchmark models and data sets that have come out in the recent years that are targeted exclusively for common sense reasoning. Especially in 2018 alone, we have a number of data sets that were specifically designed for common sense reasoning, and you will realize that most of them are targeting the task of question answering. So reasoning is necessary in performing better, especially in most of the NLU tasks, because most of the time, we will not have the solution given in a linguistic context, and there will be a lot of ambiguities in the language that we need to, our intelligent systems needs to be able to figure out. So this is one of the reasons why I chose the task of question answering for my fine-tuning. First of all, QA is one of the most important natural language understanding task that will allow us to measure how a system is doing in terms of common sense reasoning. In addition to that, QA requires a mix of language processing and reasoning skills within a single task, and that's why it's more practical than probably dealing with some other more complicated and refined tasks. In addition to that, better reasoning achieved through QA systems could be applied to a variety of systems that is not limited to natural language processing or understanding, such as vision and robotics, the examples of which we have started to see lately. So the approach that I take in my project was to analyze the patterns that a fine-tuned GPT small performance on QA task could reveal about how a language model attains and performs reasoning. So for this, I have experimented with this small model and fine-tuned it on the Stanford question answering data set. For those of you who are not familiar with the data set, I will be giving some information about that. Oh, sorry. I meant to go back. All right. These are two of the model architectures that I have worked on. The first one you see on the left is a linear classifier that I put on top of GPT-2, the small model, the first public release one. And the one on the right will be a bi-LSTM in a naive attempt to circumvent the unidirectionality of GPT-2. Most of my results will be based on the linear model because after going through a lot of hyperparameter tuning and experiments, I noticed that actual linear model performed better. For those of you who are not familiar with the SQuAD dataset, SQuAD dataset contains over 100,000 question and answer pairs, and which have answers, and it also has the 0.2 model, also has over 50,000 unanswerable questions with some plausible answers added, and if your model comes up with those plausible answers, it's still very informative about how your model is doing. In these two examples that are taken from the data sets, you will see that the question with the answer is a very factoid styled simple question, and the one on the other side, which has a plausible answer, but you cannot actually retrieve the answer from the passage that is given for that question. So my model was, these are representative of some of the questions that my model was able to answer correctly or abstain from answering because it did not have an answer in the data set. SQuAD has, in the development set, SQuAD has over 11,000 questions, and 5,000 of which is unanswerable. And because I thought focusing on the unanswerable questions and the performance of the model on this kind of question was more informative about how the reasoning and common sense working for the model, most of my most of the numbers and reports that I will be presenting today based on those type of questions. Although there are other data sets that are specifically designed for common sense reasoning, I use SQuAD because it will give me a good start to understand how such a powerful language model, although I'm using the smallest version, will perform in common sense, and what are the mistakes, what are the successes and failures that the model will make, and it will guide me to work on more complicated and sophisticated data sets going forward. So the linear model that I implemented worked relatively better in the unanswerable questions, where it was able to pick up that the question did not have an answer and abstain from answering to that. In the plausible answer section, the model was able to first abstain from answering, like, okay, this question does not have an answer, but also able to come up with the ones that it got wrong, was able to come up with the plausible answers, which was not extremely unreasonable. In this example, this is representative of the strategy that the model learned from the training. The model attends to the first few tokens in the question text when it is trying to answer a question. This repeated so many times that I was like, okay, this is definitely taking some of the attention to the first few tokens in the question text, and then trying to pull out the answer from the passage. As you can see in this example, the model predicted that the answer contained the little phrase that I put at the bottom, but the real answer, the correct answer, was the word concrete. If we go back to the original paper of GPT-2, I noticed that some of the heuristics mentioned in the paper, such as how the unsupervised zero-shot setting, the QA task was taking up on the questions like who, what, where, and when. The same pattern kind of appeared in the model that I also trained in here. Some of my observations include that the model performs comparatively better on questions that are unanswerable, and partial matches mainly consist of initial tokens from the question. And when an answer is expressed in words that are different from the question, in a way you can think about it as a paraphrasing, the model often fails to recognize it if the order of the words are different, or used synonyms or antonyms for expressing the same idea, the model was not performing very well. So for future directions, I would like to experiment more with the bigger model, which has been very recently released, and work more on the common sense reasoning data sets that are specifically designed for this task. In addition to that, I would like to work more on natural language understanding through unsupervised learning, because the main idea behind GPT-2 was also to eliminate the need to fine-tune models and create task-specific architectures. So through common sense reasoning, I feel like there's a lot that can be done in that department to see if we can actually do that. And as a long-term goal, I would like to explore the interactions between natural language understanding and other deep learning research. And with that, thank you. I'm happy to answer questions. Do you have any?
No questions? Okay.
All right, thank you.
Hello? Sorry. Hello? Okay. So good evening, everyone. Today I'm going to talk about my project during the three months Scholar program. And the project is about sentiment analysis using reinforcement learning. And before I go into details of my project, I want to first thank my mentor, Azalian, who guided me in the past 3 months with great patience. And also thanks to OpenAI, provide me such good opportunity and the rich resource to learn and to develop my project. Okay, let me introduce more details about my project. First, I want to talk about the motivations of my project. With the development of the neural network, NLP becomes a very hot topic, and because NLP can build the computational algorithms and also let the computer to learn, analyze, and represent human language. And there's a lot of NLP tasks, and among all the NLP tasks, sentiment analysis has achieved very good performance, and there's a lot of well-tuned method online. So for this project, we propose some novel models that can combine reinforcement learning and supervised NLP method to predict the sentiment of a sentence. And currently, as mentioned before, there's a lot of well-tuned and also have a lot of supervised learning method about sentiment analysis online. So we consider this project and we consider RL might self-learn and capture some missing information based on the current models. So let me talk about details about the models. As mentioned before, we propose 2 novel models that combine reinforcement learning and the sentiment analysis supervised learning method. The first model, I would say, or I would call it the sentence restructure. In the simple words, we just sample crucial words in a sentence that are useful to predict the sentence sentiment. And we can see the models here. First, the model consists 2 parts. The first is the policy network, and the second is the classification network. We can see the graph examples here for the sentence restructure. The top rectangle represents the policy network. And that means for each word in a sentence, we sample based on the policy whether to keep or delete this word in a sentence. to predict the sentence sentiment. So after the policy network, we actually pass the selected sub-sentence to our classification network. For example, we have a sentence and there's a lot of R, N, Z such words. So maybe as we expected, we may remove those words to predict the sentiment, and also the prediction will not be worse. So based on the selected sub-sentence, we pass the sub-sentence into the classification network. And for this classification network, it actually, we use the traditional supervised learning NLP method, like we've tried long short-term memory, transformer, and also pre-trained BERT. So, so some details on the right part. We can consider this sentiment analysis task as a sequential decision, and current decision in a sentence always say whether to keep or remove this word in a sentence will affect the following decisions and also affect the following predictions. And which all this sequential process can be naturally adjusted by the policy gradient method. And here we use the delayed reward. That means we cannot have the reward until we reach the very end of our sentence. Once we have the prediction of the sentence sentiment, we can have a reward with value, we take value 1 if we predict correctly, and with value -1 if we predict wrong. And for the action, as mentioned before, it's just for each word, we decide whether to keep it in the sentence or just delete this sentence. Just delete this word in the sentence and use the sub-sentence to predict the sentiment. So this is our first model. And our second model, I would call, we use the word probabilities in the sentence to predict the sentence sentiment. So instead of considering 2 networks, we are only using 1 network. And we predict the probability of each word and use the sum of the word log probabilities to train the language model and using PPO loss function. Actually, we've also tried other policy gradient loss functions. So we can also see the model structure in detail here. So it represents our word probability network. So for each word, we have the output. We can have the output tensor of the word probabilities after using the pre-trained BERT network. And then we still use the previous reward function with value 1 if we predict correctly and the value 0 if we predict wrong. So one thing we tried different with previous is here. We are not only using the forward sentence order, we're also using the backward sentence order. So in this case, we can have 2 probabilities of the word probability. And we can define the loss functions with only the forward sentence order probabilities, or we can combine using the both forward and the backward sentence order probabilities. So let's see our data set and the experiment here. So basically, we evaluate our models on Stanford Sentiment Tree Bank, which is a public data set, originally with 5 classes. But for our experiment, we adopt binary labels. So we use 1 for positive label, positive sentence, and 0 for negative sentence. And here is the detailed layers we tried for 2 models. First, for our first model, the sentence restructure, for the policy network, we use a pre-trained long short-term memory that output the action sequence tensor and also state value tensor. And once we pass the selected sub-sentence to the classification network, we tried transformer and the pre-trained BERT as supervised method. Here for the pre-trained BERT, we just use the simplest pre-trained BERT. The name should call based on case the BERT model. And then to train the policy network, we've tried vanilla policy gradient, actor critic, and proximal policy optimization algorithms. And for our second model, the word probabilities, we adopt pre-trained BERT, again, the simplest BERT model, to output the probabilities of each word, and then define the PPO loss to train the model. So let's see the result. We've tried two evaluation metrics. One is the accuracy metric. That is, we can consider as the binary or discrete evaluation metric because we have to set a threshold based on the probabilities from the softmax layer. And another evaluation metric is called the AUC metric. This we can consider as a continuous evaluation metric. So first we can see the left subfigure, and based on the transformer, when we add reinforcement learning algorithms, we see PPO has better performance compared to the transformer only. And for the BERT, we can produce comparable result. And for the right subfigure, we can see the word probability using PPO. Here, we are using the both forward and the backward word probabilities. So one reason for the lower AUC evaluation metric can be because for the embedding of the BERT, we are actually consider about the positional embedding. So that means when we take the backward order, sometimes we might have the poor performance. But that's our guess, and we haven't figured out why it has some low performance. Now let me talk about the conclusion and the takeaways for this project. So first we can see for the sentence restructure model, we find adding reinforcement learning method can improve the performance based on the transformer model and produce comparable results on pre-trained BERT. And also, I've grabbed the deleted words from the testing set based on our sentence restructure model, and most words are like a, n, z, such word as we expected. So these words are not very important to predict sentiment, sentence sentiment in common sense. And for the AUC, sometimes it shows the improvement with our models. So this may be a direction for our future like threshold tuning for the probabilities if we want to use the accuracy metric. And another takeaway for this whole project, I think there's a lot of combination with reinforcement learning and NLP tasks. But for sentiment analysis, we should admit this task is not a complex task. And also this task is a very concrete task. We just need to predict which class the sentence becomes or belongs to. So in this case, actually, with very concrete language tasks, maybe using reinforcement learning cannot have better performance compared to with only supervised learning method. But maybe for more complex language tasks, like text generation and summarization, using reinforcement learning can have better performance. And also I've read some paper during my project and find there's a lot of implementation in text generation and summarization using reinforcement learning. And the last thing, or last benefit for me is during this project, I got the chance to hand on all the supervised learning algorithms for sentiment analysis, like long-short-term memory, attention, transformer, and pre-trained BERT. And this gave me a good opportunity to build a pipeline with all this supervised learning for sentiment analysis. Yeah. Thank you.
Are there more questions?
Did you find any specific reasons as to why RL could be a better method for the text summarization?
I think once, I'm not quite sure, but my understanding that we cannot have good performance for sentiment analysis is because we are actually have very concrete actions. We just have to predict whether it's positive or negative. In this case, for very concrete language tasks, it's very hard to define a good reward function. But for text translation and text summarization, actually we can have a very good definition or very good define for the reward function. And with a good reward, it might be trainable for using reinforcement learning algorithms. Yeah, that's my understanding. Maybe more complex language tasks can have better performance using reinforcement learning. Yeah. Thank you.
Any other questions? Okay.
Thank you.
So good news, we're running right on schedule. We're going to go ahead and take a quick 15-minute break. We're going to start the next presentation at 6:45, so plan to be back in your seats a minute or two before then. And thank you all so much.
decide therapeutic treatment for disease. For example, in this situation, the doctor, at each time, doctor needs to decide whether to do mechanic ventilation or vasopressor, and the reward is whether the patient will discharged from hospital health to full health. This doesn't work. In drug discovery, researchers need to develop some new drug structure in order to cure some disease. At each stage, they start with the simplest structure, and at each stage, you need to decide how to grow this structure to some desired properties of these components. So in this situation, exploration and exploitation is really important. And in some less risky environments, doctors need to decide when and what kind of lab tests need to be scheduled. In some cases, the tests are very costly, and also it may have some side effect on the patients. So it's also important to decide some optimal sequential actions on this. Recently, there are some literatures working in this direction. Most of them are model-based. They have simulated environments, so they can get many samples. And relatively fewer papers are focused on model-free. They work with purely observational data. In this case, we have limited sample size, and the current status of this kind of research is really preliminary, and there are a lot of challenges associated with RL in observational data. I will talk about this at the end of the talk. So my project focuses on sepsis treatment in the intensive care unit. The main reference is this recent lateral paper by Komorowski, and I used the same MIMIC-3 dataset, which is a very large electronic health record dataset, and I used the same definition of sepsis cohort and the same state and action space. Different from their paper, I use a different reward design. So in the original paper, they assign a positive 100 reward to the patient who successfully discharged, and assign a minus 100 reward to those who deceased in the hospital or within 90 days after discharge. And for the RL algorithm, they use the policy iteration, and I use policy iteration as well as Q Learning. And they also use EICU dataset, which is a much larger dataset of electronic health record, but I didn't use that, and we have a little bit different in sample size. So this is the structure of my project. I call it AI Physician. So it basically, the input is the electronic health record, and the output is the optimal policy suggested by RL algorithms. So in the first step works with the raw data set and extract it to be regular processed time series. Then with this regular time series, I extract it to Markov decision tuples, and based on it, I apply several different RL algorithms. Because observational data are always measured irregularly and always some missing data in it. To deal with it, I use two methods. First is heuristic method. For example, the body temperature are measured in Celsius or Fahrenheit, so there's some basic transformation between them. This can help us to deal with some of the missing data. And I also use k-means clustering. So basically, the states within the same class, they should have similar measurements. So I feel some of the missing data using the values from the observation, the same cluster. And for interpolation, I use sample and hold method. This is basically approximate the time series using the step function, and we can use more sophisticated Gaussian process. So at the end, I'm interested in 24 hours before and 48 hours after the onset of sepsis, and I extracted the sample every 4 hours. So for each patient, we have at most 18 steps for each patient. So once we have the regular time series, we can use the data to fill in the environment. And the replay baffle is a container of Markov decision process tuples that we can feed into the algorithm. This one example is the tabular queue. The environment is used as for the that policy iteration algorithm. So we need to estimate from the samples the transition matrix and the reward matrix. And the replay baffle actually did something like transform the regular time series into MDP tuples. This structure follows the OpenAI gym design, so it's very, later, if we want to try more sophisticated algorithm, we can just replace this tabular queue with some other algorithm. So once we have the regular time series, we want to build our MDP tuples. The variable that characterize the state are of 47 dimensions. It basically includes the vital measurements of a patient and also the lab measures. These are continuous measurements, but I use a clustering method to cluster it into 750 discrete states. And also for the action, we care about two actions, the IV fluid and the vasopressin dosage administered in 4 hours. So these two are also continuous, but I put them into, for each of them, I put them into like 5 discrete bins. So there are 25 actions in total. And for the reward design, I care about 3 things. The first thing is that whether the vitals or the lab measurements stay within the desired range. So looking at the first graph, if the values stay in the desired range, we assign like 0 reward. But if it's like outside of this normal range, we give some negative reward. That's basically a penalty. And the second thing we care about is that if there is a sharp change in consecutive measurements. So if the change is smaller than 20%, then the reward is 0. But if it's larger than 20%, then it's going down and it's a negative reward. And also we consider whether this patient successfully survive sepsis or or he or she deceased within 90 days of discharge. So it's a positive 50 and a negative 50. So in the end, we have 278,000 plus tuples. And with this whole data set, we run for 100 times. Each time, we cut them into training data set and testing data set. And we learn the policy on the training data set, and we evaluate the policy in the testing data set. Because this is observational data, so we need to do off-policy evaluation. I use weighted importance sampling with bootstrapping. And at the end, we have 100 policies and associated mean rewards. So we choose the best policy with the best mean reward. The algorithm we use is, the first one is the physician's optimal policy, the dynamic programming policy with estimated probability transition matrix and reward matrix, and the standard Q policy. The weighted important sampling is for the off-policy evaluation. So we have the behavior policy, which generates the sample we have, and we have our learned policy pi1. And we want to estimate the value of pi1 from the data trajectories generated by pi0. For each trajectory in the sample data, we define this likelihood ratio as the ratio between how likely this sample can appear in the by following the learned policy, and the likelihood of this sample showing up using the behavior policy. And then we define the weighted importance sampling estimator as this part is the true reward of this trajectory. And this is basically the likelihood ratio between how likely it is appeared in the learned policy or the behavior policy. And finally, this one is the estimator for one trajectory. So there are n trajectories in the entire data set. So we take the average, and then this the value of this learned policy. This is the convergence of Q learning. We can see that after a few steps, the difference between sequential Q value and also the variance decrease. And this is the Q table we learned for different policies. We can see that the physician policy concentrates on 5 actions. So the x-axis represents the actions taken, and the y-axis corresponds to the different states. And you can see that for action 0, 5, 10, 15, this is the action code. They correspond to vasopressin 0. That is the lowest dosage of vasopressin. It shows that the physician's policy prefer low value of vasopressin. But the DP policy and Q learning is more diffused over these different actions. This plot shows the distribution of different actions over 750 states. Again, we can see that this is the vasopressin dosage. The physician's policy mainly focus on the no vasopressin dosage, but the DP policy and the Q learning also suggests higher vasopressin dosage and the lower dosage of IV fluids. We also compared the value of different policies on trajectories. So the mean reward for the DP policy is this value, and for the Q policy is this value. We can see that the Q policy gives higher reward on average, and also this the x-axis corresponds to single trajectories. So the x-axis corresponds to 50 different trajectories. So we can see that for each trajectory, so basically it shows that Q Learning gives much better results. And so the fundamental challenges arise from the fact that we are working with observational data. So we have limited sample size, and also we have to work with off-policy algorithm, and how do we estimate the policy from samples generated by a different policy. And in the medical application, there's also partial observation. There may exist confounding factors, and also how to design a reward function so that we can encode domain knowledge to help guide AI physician to do better decision. And future works is also related to these problems. So an immediate thing we can do is we do more sophisticated data interpolation, for example, with Gaussian process. So in that case, we can sample more frequently. In this case, we can get more data points. Then we can use some more sophisticated method. And also, there's model-based LR. If we can estimate the environments, then we can simulate this more samples. Then we can also, again, use some deep LR deep algorithm. And another two is related to off-policy evaluation and the reward design. So that's all. Thank you.
Any questions?
Hi, thank you for your talk. This was very interesting. Can you go back to the example you gave with regards to vasopressors? Yeah, okay, great. Do you know if there's anything that you've seen in the Mimic3 literature about this behavior by the doctors? I'm just curious if this has been mentioned, if you saw this mentioned either in the original paper that you were citing from Nature Digital Medicine, or something about this kind of behavior. I mean, because I'm assuming that if you don't have, even if you have a different reward, something like this, when you're taking the action you might take, this might have something, you might see something related to this. I'm just kind of curious about how you would interpret this sort of behavior.
Right. So in the lateral paper, they actually mentioned that according to some medical research, they also found that the doctors tend to use less vasopressor dosage, and this case is also an active research area in the medical field. Yeah.
How do you come up with rewards? You had chosen positive and negative 50. If you choose other things, will the policy change?
Yes, I think so, because this we encode 3 different things. If we increase the magnitude of the final for the outcome at the final step, then the weight for these two, the vital normal range of vitals and sharp changes will discrete. The weight of them will discrete. So it's a very.
How do you verify, with doctors or their expertise or whatever,
whether it's a good reward or not, right?
Right.
Yeah, that's a very good question. I think for now, it mainly depends on the doctor's domain knowledge, right? Or we can experiment with the observational data to see, to do some back testing on the observation data to choose the best design. So it's a compilation of domain knowledge and some testing, cross-validation or something like that.
I went to AI and Medicine conference at Stanford some time ago, and there was a researcher who was arguing for doctors against using black box models in medicine. I saw some visualizations, and would you say that your model is less black box, or because you're definitely able to see some values inside of the model, so it's not black box, right?
Mm-hmm. Right. So for the reward design, you can actually put some domain knowledge in there. So it's not that black box. And then because this works with tabular learning, so it's like I think it's the easiest algorithm on the RL. So it can offer some insights into the data and the situation. But I think if we want to use like more policy gradient or DDPG, then it may not be able to offer some intuitive interpretations. But this is also an active research area.
Thank you.
Thank you.
That's all that.
Can everyone hear me? Great. Well, welcome everyone. Thank you all for coming this evening. My name's Edgar, and I'm going to be talking about knowledge distillation for transformer language models. Just to give you an overview of what I want to be talking about, I'll introduce the transformer, its successes and limitations. I'll give you some background about knowledge distillation. I'll give you an interpretation of what knowledge distillation can mean in this context. I'll give you guys the approach that I took. I'll outline some future work that can be done, and I'll have some time for some questions. So the transformer model is latest and greatest, one of the latest and greatest neural networks that have just come out. It's very powerful. It can generate language like a human being. It can answer questions. It can summarize texts, and so much more. And so it's very powerful and very exciting to me because I wanted to make resources for people who might not necessarily have resources. And one of the ways to provide resources to people is through human language. And so when I was starting to play with these models, I ran into some trouble. And that's that they're huge. My little MacBook was huffing and puffing and crashing with memory. And so I couldn't imagine what would happen if I tried to run one of these on my phone. And so I was hoping to try to compress these models and make them smaller while still having similar levels of performance. And I was going to give you guys a little quick introduction to the transformer, but my peers have done such a good job, I'll skip past that and tell you guys about what knowledge distillation is. So knowledge distillation is getting a larger, well-trained teacher neural network to teach a smaller and untrained student neural network by getting the student to mimic the outputs of the teacher. If we say that we give them both models the same input and they give about the same output, we say that the student model is performing about just as good as the teacher, even though it's smaller. And in this specific context, something that what happens when we do knowledge distillation is we give the neural network a sequence of words, and we mask some of them. And usually we have a loss function because when the transformer spits out its output, it gives a probability distribution over words. And the goal is to try to guess the word that is being masked. And you want to minimize this, so you want to get the word right. But in knowledge distillation, we're able to provide the student network so much more information by giving it the output of the teacher. So in this case, the output of the teacher is a distribution over words, a probability distribution, as opposed to just a label, which is 1 for the correct word and 0 for the others. And so what this distribution does is give a probability over reasonable words, which will distill some knowledge into the small network. So the man went to the blank. The right word is store, but if the larger neural network is able to give the student the information that another possible reasonable word is groceries or bakery or any other synonym, the student will be able to learn a lot more and hopefully be able to spit out the similar or same distribution over words. And some more interpretation as to what this means. We have this idea that the neural networks have a certain solution space, and if we believe that we can distill knowledge to the smaller network, we believe that the smaller student network can inhabit a similar solution space as a teacher, and we see that happening. And sometimes that happens, and sometimes that doesn't. So, to give you an example of in the case where like a function can inhabit a similar solution space to another function, but it doesn't necessarily do that, is in this simple case of curve fitting. The green curve can encompass every single, which is a much higher order polynomial, can encompass every single solution and represent this function and so much more because it has all these higher order terms. But it usually doesn't, even though its solution space is much larger. And that's because it doesn't have the right inductive biases to find that solution that we're looking for in the current way that we train that model. And so the hope for the student and the teacher transformer models, the idea is that the larger transformer can represent a larger solution space than the smaller one, and the larger transformer converges to a particular solution space, and the smaller transformer converges to another different solution space. And by training these, the smaller network on the larger network, we get the region of convergence in solution space to get more closely to where the larger model is, so that they can represent the similar, if not same, transformer by spitting out the same outputs, despite being a different model with different weights and different sizes. And so my approach to this was taking BERT, the bidirectional transformer, and instead of having either 24 layers or 12 layers, I went with 9 layers, and I wanted to reduce the dimension of the vectors that it works with to 576 as opposed to 768 or 1024. And this initial approach proved to be awful, actually, initially. I had an accuracy of about 5%, even though I trained for 32 GPU days. And upon closer inspection, it kind of makes sense. Because I ended up with about 72 terabytes of data. Wikipedia was initially 12 gigabytes of text. But by saving the outputs of the student, or of the teacher neural network, I ended up with a ridiculous amount of data, and too much data for the GPU. It was not able to handle long sequences. And that's because as opposed to each word having a label, I ended up with this huge vector giving a probability distribution for over the words, which is 3,522 size vector. And so I had to think of something different because it wasn't going too well. And so I thought about the outputs of that teacher neural network and realized that most of the information in that distribution is not very useful. If we think about a masked word and consider a 30,552 vocabulary, most of those words are not going to be synonyms. Most of them are not going to be important. And upon looking at them, most of them had a probability of like 2 to the negative 8, something very small, not useful. So I decided to instead truncate the output of that teacher neural network and only consider 10 words, which left me with 384 gigabytes of data instead. And with the time that I had, which was about 8 GPU days, I was able to get an increase to about 7%. And so this leaves an exciting work of scaling this. The big dogs, some of them sitting right here, trained their neural network for 2,048 TPU days or 240 GPU days, which is a lot. And so it leaves a very exciting opportunity to scale up this task and see if we can have a similar performance. I'd like to thank my mentor, Susan Zhang, wonderful guidance. The rest of the OpenAI Scholars for providing me with a lot of support, and Maddie Hall, who was able to organize all of us despite juggling like 20 other things at the same time. Thank you.
Questions at all? No questions? No questions. Okay.
Thanks.
Thank you so much for the support, everyone here listening to us. I say I cannot. Well, okay. And thank you so much for AI, for this OpenAI, for this opportunity, especially for my mentor, Kai Akrulmaran. And so before I start, I'm going to talk a little about myself. So I was a software engineer in my previous life. I was doing network security, and after that, I decided to move to education. And I have been doing tons of things with education. Right now, actually, I started a program as soon as I joined OpenAI to try to convince 60-plus-year-old people that AI is important. It's just for Spanish speakers. And that's the picture of the group. Right now, one of the guys, Rodrigo, is taking the lead, teaching them TensorFlow through Udacity, so I'm very proud. But I also do other things. I do kids and teachers. That's me at Columbia showing the GPT-2 unicorn example to some very interested teachers. So my motivation behind this project is that I think education is completely broken. I think it was badly designed right now, schools. And the best way for us to learn, and this is what science is telling us, is to do projects, right? The way that we're doing this program is to go there, dive deep into a subject, and do something that is meaningful for us, and is apply knowledge. But schools cannot use it. Why? I actually am on the founding team of a school in New York, because there's no curriculum for project-based learning. There is no time for the teachers to learn how to do themselves projects. And if you have many projects in a school, in a classroom, many kids doing projects, it's a mess in the classroom. And the poor teachers are actually implementing these things in the classroom, spend tons of time looking for resources on the web, adapting them, and trying to, customize them to a classroom. So right now, AI in education is just tracking. It's just trying to see how we can personalize learning. But what if we can actually unlock the educational content in the web? So this is a proof of concept for that. So this is my model. It's Creature. So Creature, what it does is that it was trained on data from the Exploratorium here in San Francisco. Actually, they have a great data set of activities that are kind of projects that are used just for learning and inquiry. And they have 3,700 of these activities. So I trained BERT. Oh, I'm not going to explain BERT because I think someone before me already did that. So I trained BERT to actually use another data set that has 280,000 projects, DUI projects, meaning like how to build a bicycle, how to cook enchiladas, or how to create a robot that will tell me if I need to water my plants. To tell you what projects do you need to do to learn something in particular, like in this case, biology. So what did I choose? Instructables. So, I have to collect my own data, which, Jesus God. But the thing is that Instructable is a marvelous website with very well-documented project. But the goal of this is not to learn, is to make something that is functional. So if you put in the search, like, I want to do biology, it just returns 12 projects. And 3 of them are actually not related to biology. But they have great, great projects. So with Creature, we can actually get 200 projects. And because of the way that I train it, we can actually get projects that have explanations on them. So I'm just going to read the first paragraph of this project. It says, what does your heart sounds like? How fast is it beating? What's the pattern? A few students may be able to detect woo-whoomp part of the beat, which I have probably heard in movies too. This has to do with the fact that our heart has 4 chambers, which we will get to soon. This comes from 2 pairs of valves in the chambers of the heart. So this Instructable was actually meant to be done by students. And we have many of these in the search. So right now, the model is doing 30 to 50% depending on the label that have explanations from those 200s. So how did I do this? So the way that I did it is I took all the data from the text of all the activities from Instructables, and I divided between 4 things. Descriptions, instructions, explanations, and tools and materials. And with that, I trained BERT to actually predict what will be the learning topic. So each of these exploratorium projects, they have some labels of what will you learn. And I end up having 50,000 examples. I trained BERT for 2 epoch, 9 to the -5 learning rate. And I took 20% of that for validation. I got very good accuracy. So I decided to try it on the Instructable data. So on the Instructable data, again, I took the task. I chunked it into 512 tokens. And then I predict with that, what will you learn to do it? So it was good. The result was kind of good. But then I developed this interface to do active learning. So what I do with this is that I get the chunk of the text that I actually match. And then I can say if it's positive or negative. And with this, I improve it a lot. And to get a bit more validation, I use the UMAP library, that is a dimensions reduction library, to try to see what's happening under the hood. So this is a visualization of the topic physics. We can see on the purple, we can see something, yeah. So on the purple one, that's mechanics. On the blue one, that's electricity and magnetism. And between them, kind of sound is bridging those 2 clusters. The orange is light. And there is a tiny little bit green there that is intersecting with sound that is waves. So actually, waves somehow are very far from sound. But it's very interesting. This is I'm very interested to exploring what's happening with these embeddings. So I hope that by now I convince you that AI can be used for something else besides tracking in education. I will be very interested in trying to do a web app where you can also filter these projects by tools and time that you have. This was my 8th experiment. All the rest didn't work very well, but one of them that was promising is trying to see what is the expertise on these projects. And I use another data set from Hackster, so I'm very interested in developing levels of expertise on these kinds of things. And so I'm right now looking to something to keep feeding my Creature. So if you know of any grant or something that has to do with AI and education, I would be very interested to hear it. That's it. Thank you.
Any questions?
Did you ever think about using video?
Yeah. So I actually, that was one of my first options, trying to use video, especially from TEDx. They have very cool content. But I started using pictures, actually, and it wasn't very promising. So then I got a little bit scared about trying video, but I think that's one of the things that I would like to try.
No other questions? No other questions? Okay, thank you.
from a paper by Borgi that looks at all of the different GAN metrics that we have. He evaluates over 24 quantitative measures and 5 qualitative measures, all of which are at times used to evaluate GANs, none of which are optimal and none of which are the Tolkien metric that can tell us everything we need to know. So the two most quoted scores you'll find around GANs are the Inception score and the Fresh Air Inception distance. Both of them are based on state-of-the-art classifiers, Inception by Google. And they look at, in the Inception scores case, they look at marginal entropy of, or marginal distribution of labels. In the Fresh Air Inception distance case, they look at taking real and fake samples, putting them through inception layers, and at the max pool 3 of V3, look at the difference between mean and covariance. It gives us an idea, but you come out with a scalar value. So if I said to you, I have a GAN that's got a scalar value of 8 and one with 40, I'm not sure you could tell me kind of what that means other than a lower score's better in FID. Similarly, in March, researchers from here at OpenAI and Google released the Activation Atlas, which gives us an unprecedented ability to look inside neural networks and visualize what's going on inside the black box. So for my project, I wanted to look at what would happen if we tried to bring these two things together and evaluate GANs using the Activation Atlas. So in terms of the project, I needed a whole ton of samples. Thankfully, Big GAN, the mammoth and current state-of-the-art GAN, released their fully trained ImageNet generators. So I was able to use Big GAN as one set of samples. And then SN GAN, which is the spectral normalization GAN created by Miyato and others, was state-of-the-art a few years ago and brought a lot to the field, especially around normalization. And it had a FID score of around 27. And they also open sourced their fully trained ImageNet generator, and so I was able to do it. So we're considering here real images from ImageNet and GAN samples from Big GAN with a FID score around 8.7 and GAN samples from SN GAN with a FID score around 27 to see what we can find. I then took the Inception V1 network. I used V1 to be consistent with the work of the original Activation Atlas paper. For clarity, I should note that the Fresh Air Inception distance is most often calculated on the V3 network. However, Big GAN actually used V2 for their calculations, and SN GAN used only 5,000 samples for theirs. So it gives you a sense of how difficult metrics are in this space. Having done that, passing all of these samples through the Inception V1 network across 9 layers and capturing activations. You've got hundreds of thousands of activations, right? Massive amounts of dimensions. To bring that down to something that we can kind of comprehend, and at least I can, used UMAP to dimensionality reduce to 2D. And having done that, we can then apply a grid over our dense scatter plot to find meaningful kind of grid clusters. Having done that, we then need to generate icons for each of these grid cells. So a grid cell will contain a number of related activations. And the part that really brings the activation to life, Activation Atlas, is creating these feature visualizations which give you a visual view of a direction in activation space. Having done that, we can then also calculate the KL divergence between distributions, right? Because these grid cells give us a sense of density between the different distributions. And then lastly, we can create some atlases. And in this case, in contrast to the original Activation Atlas, each grid cell in the Gantless will not only have the feature visualization of the grid cell, but also a bounded colored border, which gives you an indication of the log likelihood between two distributions. So this particular example is comparing Big GAN to SN GAN, and the dark blue around the border means that in this square, Big GAN has a much higher density. It also has at the top the count of the samples in the square, so you can see how many instances of samples from Big GAN versus SN GAN were in that square. And on the bottom, we have an indication of the maximum logit, which can give you an indication of what that grid cell is doing in regard to softmax at an indicative level. Lastly, you've also got a grid swell reference, which I find really helpful when we're trying to talk about these squares and identify them. So just very briefly, I've implemented visualization of these icons very much in keeping with the original paper, and found like them that in regularizing these icons, it was really whitening, as you can see on the far right of the slide here. That did the most to ensure that we had as much detail and kind of visual fidelity as possible. So what did I find in terms of the difference between all of these distributions? And again, don't worry about getting the numbers on here, but broadly what we find was really interesting is if you compared Big GAN to ImageNet layer by layer, the biggest divergence between those two distributions actually occurs right at the beginning of the network in mixed 3A and 3B, which is kind of surprising in a way to me, because early on in an inception network, the network is looking at very low-level detail, right? It's looking for shapes, texture, kind of brightness, and so forth. And one would presume that that might be very, very similar no matter which distribution you're putting through. And I'll talk a little bit about what that may indicate. Then if you wanted to look at where do we see the biggest difference between big GAN and SN GAN, if we're trying to compare how good those two distributions are, where do we see that? Well, actually, if we change the heat map to remove those first layers, we can better see the differentiation. It's not being kind of watered down by the first layers. And actually, it's right there at mixed 5B at the end in the bright red. SN GAN really in the later layers doesn't match the ImageNet distribution nearly as well as big GAN, and that's where we can see some of the differentiation. So what I'd like to do now is just give you a few examples from mixed 3A and mixed 5B to bring it to life. So this is the activation atlas, 40 by 40, big GAN versus ImageNet for the first layer in the network. And what you can see is that each of the icons is not an image that you might recognize, right? We're not seeing dogs or cats at this level of the layer. This is where we see texture. But what you saw is on one side of the map, we had that blood red area, right? A huge divergence. And so if I look at cell, say, 1511 in mixed 3A, what we saw there is, if you can see, there's 1,302 samples from ImageNet that fit into that grid square. But 0 samples from big GAN actually go into the grid square. So we're seeing already a huge divergence. And when you look at the data set examples of what the network is picking up in that grid square, it's looking for highly detailed textural areas. You can see it's not just grass up the top with a very cute puppy that wasn't actually the spatial activation. The grass is like long fronds of grass, right? At the base, you can see on the far right a placemat and a manhole cover with very detailed, intricate texture. And actually, the two labels most represented in this grid cell were hay and manhole covers. Manhole covers surprised me at first, but when you look at them, there's actually, it's over there, right column, second from the bottom. Manhole covers actually have a lot of texture in the asphalt around the manhole cover itself and on the metal of the manhole cover. So we're seeing a lot of texture. So the question for me is, well, then where did all the big GAN hay and manhole covers go, right? Where would they be? And so it actually led me to go all the way to the other side of the map to cell 2032. And that's where you start to see dataset examples from big GAN and a divergence between big GAN and ImageNet. So you've got way more big GAN examples in this cell than ImageNet. And what we can see are a lot of the same themes. So we've got hay, we have grass. In the bottom, you even see a grey sweater, which is kind of evoking that same idea of really detailed grey texture. But the fidelity of the texture here and the level of detail is much less. And so already the activation atlas has shown how the network is massively kind of separating these. And I think at 3A, you see both big GAN and SN GAN exhibit this same kind of quality. And I think it's telling us more about the difference between the fidelity of images, especially GAN samples. I was putting through a 128 resolution. And if you took, say, the 512 big GAN, I'd be interested to see how this may change. So then the question I think that's really interesting is, can the activation atlas tell us something more about how big GAN differs from SN GAN? Where do we see that? And for that, we need to look at layer 5B, which is right at the end of the network before you hit a softmax, before it's finally classifying. And so for this one, I'm showing the activation atlas at mixed 5B, 40 by 40 grid. The coloring is showing you in red cells where SN GAN has a much higher density. In blue, cells where big GAN has a much higher density, right? So what's this going to tell us? Well, the first thing it sent me to was cell 223, which has a very big density divergence. And what's interesting about this cell is it's looking for the Entelbücher dog, which I didn't know, but is like a Swiss mountain dog, very brown, white, and black, and it has a very specific look. And in this cell, there's only about 22, 24 examples of both ImageNet and big GAN, but they're very well-structured, well-formed shapes with very clear details and snouts. And interesting in this cell, SN GAN didn't manage to have any of its samples recognized. And I think what we'll see as we go through some of these examples is the same thing playing out. Big GAN has both a self-attention mechanism, which allows it to maintain a much better sense of global structure. as well as the mass scale of the batch sizes it put through, allows it to maintain not just good texture in its samples, but also global structure. So if you go to cell 3520 and we look at cocktail shakers, something that I don't think we talk about nearly enough when we look at GANs. But this is a really interesting cell for me because there's 328 big GAN samples in here. In this cell, ImageNet hits a similar kind of density, around 269, but SNGAN only has 61 samples picked up. And if you look to the far right of the slide, which are the SNGAN samples, you can see that it's struggling to maintain the outlying shape, that structure, and only kind of picking up on some of the shape cues. And if you go to cell 2122, now I'm not here to tell you that Big GAN has solved the uncanny valley, but this cell is looking at MALO, or one-piece bathing suits. And what I find fascinating about how this has been picked up by the atlas is that both ImageNet and Big GAN in this cell have around about 150 samples, which all represent the bikini or one-piece bathing suit, right? And if you think about in ImageNet terms what it's looking for some sand, some water, a lot of human skin in the image, right? And maybe a piece of material. SNGAN manages to hit those themes, but they're very textural with very little shape and distinction. In contrast, Big GAN, and can I use this? Yeah. You can actually see it's actually hit the shape of a triangle bikini and a one-piece MALO, which in comparison to early GANs, which could only really do skies and broad textural things, the ability to pick out individual shapes in such a complex area is pretty phenomenal, and you're seeing that play out. So one of the questions I then had, the ever-ending one, is, well, where on earth did all the SNGAN samples go, right? If we've got all of these cells where Big GAN is at the same sort of density as ImageNet and doing well in a distribution term, where did SNGAN go? And that sent me to the bottom of the map to cell 316, Weasel cell. So the Weasel cell here is looking for things that are kind of white or caramel and fluffy and don't have sharp edges or very defined kind of structure. You see things like polar bears turning up. The second image there on ImageNet might be a little confusing because it's a scooter. But the part of the image that was spatially activated was actually a fluffy sheepskin rug at the back of the scooter, and that's what it picked up on. So that's the sort of thing you see in this cell. And both Big GAN and ImageNet have sort of densities there. SNGAN, in contrast, has 2x the density of ImageNet in this cell. And while at first you see some of the similar sorts of themes, polar bears and fluffiness, if you actually look through the rest of the dataset examples, you start to see, and sorry, it's quite small here, but what you actually see are a whole lot of examples from non-Angora fluffy classes, whether it's dogs or even inanimate objects like buildings that have so much artifact and kind of overexposure in the image that they're lumped in here and picked up by the classifier in this area. And so for me, what's really interesting here is that it helped for me characterize a couple of things. One, what on earth does a FID score of 8 versus a FID score of 27 mean, right? At one level, I know that the mean and the covariance of a distribution is getting closer at 7. But what it's also kind of helping me see here is, okay, if I look across the activation atlas, while Big GAN and its shape, capacity and fidelity is allowing it to hit many of the same grid squares in a similar-ish density to ImageNet, SNGAN is hitting some of them and then having these clumps of clusters in kind of amorphous areas, and that's helping to do it. The other thing I found really fascinating about using the atlas to understand it is when I first created all the samples for SNGAN, honestly, I freaked out a bit because I looked at them and I was like, these aren't good enough. This doesn't look like SNGAN. And what I realized is I was used to looking at SNGAN samples in contact sheets that showed me 10 images all from one class at a time. And my human eye, when seeing 10 images all from the one class at once, would infer structure and infer a kind of meaning in those images that the classifier may not well pick up. And so that's something that I thought was really interesting about using this as a way to guide which samples to investigate and so forth, because there's always an element of going back to the samples in GANs, and so this can help accelerate that. So lastly, future directions. Obviously, there's about 81 activation atlases if you think of number of grid cells, grid size by data distributions by options. So working on an interface that would allow us to do that. We can extend samples, some non-GANs. I'd love to put the sparse transformer through this. There'd also be an opportunity, I think, to keep samples the same, but actually rip a discriminator out of a GAN and actually use that and sort of track how different samples are being evaluated by a discriminator through. And similar to the MIT SAIL work on GAN dissection, it would be great to take a generator and look layer by layer, how is that generator doing what it does. So lastly, I do want to thank everybody here. Thank you for staying till the end of my talk. But thank you to OpenAI, Christy and Maddie, amazing and helpful, and to Chris Ola and Ludwig Schubert from the Clarity team, have been amazingly open with not just their time, but their knowledge and wisdom, which has been phenomenal. And it's been a blast, my fellow scholars, so thank you.
No? Any questions?
Thanks. This is super exciting work. Can you explain a little more about how you got to the slides you presented at the end? Like, what motivated? Like, because you mentioned that this is a really big activation map. So, like, I mean, activation atlas. Like, how do you
pick cell 223?
Yeah, exactly.
Yeah. So I tried as much as possible not to cherry pick and just look for things. So the way I looked at it was to take the log likelihood of each cell and literally rank it and go for the ones with the greatest divergences, the greatest difference, and interrogate those first from both ends, both from where big GAN was really overweight and then where SN GAN was really overweight, and compare and come at it from those angles. Having done that, once you're inside a cell and you start seeing something like, you know, all the hay labels seem to be here, then I would sort of say, okay, where are all the hay labels for the alternate distribution? Because that can give us an idea of almost, for mix 3A at least, I almost think about it as twin grid cells, right? Like, how are these related? And try and look into it that way. Does that help?
Tom.
With Big GAN, I know that in the paper they had like a truncated link trick. Did you try visualizing that for?
Yeah, the truncation trick, if no one's heard of it, is very cool with Big GAN. It's, you can truncate the values of the normal that's used for the noise vector before they develop the samples. And in effect, if it's very, very low, you get a small variety of samples coming out, but amazing fidelity. It's almost like the guys themselves say, it's almost like cherry picking your very best options. Or if the truncation's very high, you end up with large variety, not so great samples. These were all done at 0.5 truncation at a midpoint. I did some early work on looking at the truncation, and you kind of saw gratifyingly what you might expect, which is as the truncation blew out, it just kind of, and decreased, everything just kind of exacerbated, right? Things that were not going so well got worse, and so on and so forth. But it's in that sample extension bucket, and I want to do some more because it's fun. Yeah.
Any other questions?
Everyone's got a question.
Sorry.
Yeah.
This is really awesome. I'm wondering, independent of the comparisons between the two GANs, I'm wondering just what were your overall thoughts on how well Big GAN compared to just the ImageNet distribution?
Yeah, so, well, right? Can I not make people sick? So if you look at, apologies, guys. If you look at the KL divergence by layer, if we can get there, so on this slide, what you can see is Big GAN versus ImageNet is our first one, right? So if you discount layer 3A and 3B for a moment, actually all the way through you've got pretty good kind of tracking between ImageNet and Big GAN, and you only see a lot of the divergence at 5B. So I really want to rerun this with a much higher fidelity Big GAN sample, because a lot of the best Big GAN stuff that you see, those quintessential examples, are coming out of their 512 resolution, and this is only done at 128. So I think that you would see an improvement there. And it's only in those later layers, and it's very specific. Unlike SN GAN, where you're seeing kind of broad issues with things being lumped into grid cells, with Big GAN, it seems to be specific to categories, those categories that require more structure and so forth. Does that help?
I'm wondering, like, if everything were blue, would that mean that this is just like a totally
So if everything were blue, it would mean that your KL divergence is close to 0, right? Which means that the distributions are quite close. The issue with using the Inception classifier network is that saying the way in which the classifier network understands your images with the purpose of classifying them, they are very, very close. So you have then tipped over the balance that your swimming suit is recognizable as a swimming suit. But having a classifier give you a complete accurate score on being a swimming suit does not mean that it is photorealistic to human eyes. So it's getting you a part of the way there. But if you want to do a comparison for like photorealistic images, classifier alone does not do that.
Any other questions?
For real this time? Awesome. So for people who might have thought of questions during the break or just want to chat a little bit more informally with some of the scholars as well as the mentors, we will be here till around 8:30, and we can just mix and mingle over in the living room as well as here. But one more round of applause for all the scholars. And thank you all for coming and watching the presentations with us.